Pluto, a distant and confusing body, was once considered a singular and genuine planet, an individual member of our planetary family. However, recent disturbing verbalizations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astonishing revelation. They suggested that this cool world is on a possible collision course with Neptune. But how could this happen? And what might be the consequences of such a colossal event? Are we witnessing a fascinating impacted whimsy, or is there something more to this approaching limitless incident? Join us as we explore the possible outcomes of a Pluto-Neptune impact. Pluto, a former planet that was relegated to a more modest status, remains a subject of interest and study in the cosmic community. According to persistent figures by leading experts, Pluto's orbit is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Shokaku are raising the alarm about a potentially hazardous disaster between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unusual compared to any other planet in our nearby planetary system. It takes an astounding 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even finished one full circle. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly eccentric shape, very different from the nearly round orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is much more erratic compared to other planets. This inclination and irregularity add layers of complexity to its orbital pattern. Perhaps one of the most captivating aspects of Pluto's orbit is its interaction with Neptune's orbit. For at least 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, contrary to what we would expect from their positions in the planetary system. This leads to the obvious question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The evaluation of Pluto's orbit began shortly after its discovery at first. Space experts struggled to explain its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood apart. With its hazardous inclination and erratic shape, the mystery surrounding Pluto's orbit can be explained by the three-body problem in celestial mechanics. This is about understanding how three objects in space, such as Pluto, Neptune, and the Sun, move and interact with one another through their gravitational forces. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex way. Terms like asymptotic libration, scope libration, and the VZK wobbling are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a type of libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from affecting each other. Degree libration, on the other hand, refers to the vertical motion of a celestial body in its orbit. For Pluto, this suggests that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an additional layer of protection from potential collisions. Another critical factor in this situation is the VZK wobbling, named after three scientists, VALV and KU, who studied how objects move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move, and in Pluto's case the VZK wobbling helps us understand why its path near the Sun is so unusual despite the apparent randomness. This impact helps keep Pluto's orbit stable for an incredibly long period of time. The VZK wobbling shows that although things in space might seem chaotic and inconsistent, certain patterns and forces help maintain order. These factors help keep Pluto's orbit intact, ensuring it doesn't crash into Neptune or veer off course. This three-body problem affects how we understand these orbits, particularly in how space objects pull on one another. Focusing on this helps us study Pluto, our neighboring planetary system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that despite these predictable properties, Pluto's orbit is still wild, with small deviations in initial conditions leading to significant differences over long periods of time. However, these strange characteristics of Pluto's orbit have been found to maintain consistency over extremely long stretches of time. Later computer models have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune is not the only factor. Jupiter's gravity also plays a significant role in safeguarding Pluto's orbit, and Saturn also helps in that broad region. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady course for an incredibly long time, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue orbiting safely in space without running into trouble. These irregularities are crucial in the larger context of the universe for maintaining the stability and consistency of celestial bodies. Without these factors, our nearby planetary system, as we know it, would be a place of far greater turmoil and instability. Bodies like Pluto could indeed crash into others or be ejected from their stable orbits, triggering a cascading effect on other celestial bodies. For Pluto especially, with discussions about it potentially crashing into Neptune in the future, understanding its orbit is critical. This gives us a clearer picture of the dynamic nature of neighboring planetary systems. The case of Pluto shows how even in the most apparently unstable orbits a balance can be achieved through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of consistent observation and study of these anomalies to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The idea of orbital resonance, which implies the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computer simulations has been crucial for research to understand how Pluto moves in space. These models use complex mathematics to simulate how Pluto, along with other space objects like Neptune, pull on one another by altering small details in the simulations. Astronomers can see how even minor changes can have a massive impact on where Pluto ends up. In the late 1980s, these simulations revealed something quite fascinating about Pluto's orbit. Despite having systems like asymptotic libration and extends libration to stabilize it, its orbit can still be wildly erratic if you start with even a slight difference in where Pluto is or how fast it's moving over many years. It's path could end up looking completely different. Despite this chaos, Pluto's orbit remains stable for billions of years. This suggests that Pluto's journey around the Sun has a certain order to it, even though it seems turbulent at first, especially when it involves erratic orbits like Pluto. This presents enormous challenges. The inherent nature of these systems suggests that long-term predictions are often filled with uncertainties, while numerical simulations are an essential tool for understanding and predicting the future behavior of celestial bodies. They also highlight the limits of our forecasts. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or deviation can drastically change the results, making precise predictions an overwhelming task. Additionally, the turbulent nature of large orbits like Pluto's serves as a reminder of the ever-changing and dynamic nature of the universe. While we've made enormous strides in understanding space, Pluto's example reminds us of how our understanding of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the nearby solar system. It shows how the presence and position of each planet can have using effects on the stability and direction of other bodies within the system. So why are prominent astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune? Despite all of these complex forces working to prevent such an event, Neil deGrasse Tyson, a famous astrophysicist, offers a book-length perspective on the mysteries of our nearby solar system, particularly the fascinating example of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. His stance on Pluto's renaming is framed in the ever-expanding knowledge of our solar system. He views the renaming not as a diminishment but as a necessary shift in accordance with our growing understanding of the many bodies surrounding our Sun. Tyson's approach to celestial mechanics is one of continuous learning and transformation. He sees the complexity of Pluto's orbit as well as its interactions with Neptune from a perspective that acknowledges the volatility of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still have to discover about the forces shaping our solar system. In the grand scheme of things, Pluto's orbit is a fascinating case study in the intricate interaction of gravitational forces within our nearby planetary system. While its orbit is stable right now, the mysterious dynamics between Pluto, Neptune, and the other planets suggest that even the most seemingly stable orbits could change over time as astrophysicists like Neil deGrasse Tyson continue to investigate the mysteries of the universe. They help us better understand the fragile balance that governs the movements of celestial bodies. The potential for a Pluton-Neptune collision is not necessarily inevitable, but it serves as a reminder of the constantly evolving and puzzling nature of the universe. Despite the established theories surrounding Pluto's orbit, it's important to consider the broader implications of these dynamics for how we understand the nearby solar system and the universe at large. While Pluto's journey is one of intrigue, it is also a reminder that the universe is filled with mysteries and complexities waiting to be explored. The concept of orbital resonance, especially between Pluto and Neptune, is a central piece of the puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2 to 3, is a fundamental aspect of Celestial mechanics for every 2 orbits. Pluto completes around the Sun. Neptune completes 3. This resonance ensures that despite their orbits crossing the 2 planets never collide. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic impacts. The importance of resonance in maintaining stability cannot be overstated. It provides an excellent example of how systems in space, even those that initially appear chaotic, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its irregular orbit, has remained stable for billions of years. This dynamic is a key aspect of the larger structure of the nearby planetary system. The impacts of planets like Jupiter, Saturn, and even Uranus are vital in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its immense gravitational power, acts as a sort of guardian for the interplanetary system by influencing the paths of other asteroids and dwarf planets, including Pluto. In fact, some researchers speculate that Jupiter's gravity might have prevented Pluto from being ejected from the solar system entirely. Without Jupiter's protective influence, Pluto's orbit could have been disturbed even further, possibly sending it out of the Sun's gravitational reach. If